This is the video for chapter 27 in our textbook, and it's about the wave aspects of light. We've talked about the ray aspects in which light propagates and interacts with large objects such as mirrors or lenses. Here, instead, we talk about what happens when light goes through very narrow slits or holes or things that are roughly of the size of the wavelength of light itself, and then the wave nature of light manifests itself. Just as a reminder, we have an important equation that relates the speed of light, the frequency, and the wavelength. And the first use, or the first place where we get to use this is something we did already with the index of refraction. And we know that in any medium that is not vacuum, light will conserve its frequency. That's kind of a given. How things oscillate doesn't change because you change medium, but what will change is the speed of light and the wavelength itself. So we have this expression, which gives you the new wavelength in a medium with index of refraction n. And we also know that we have this relation between the speed of light in a given medium, v, the speed of light in a vacuum, and the index of refraction, n. So the speed is given by c over n, and since n is always at least 1, the speed of light in any medium other than vacuum is going to be less than c. The next thing we want to do is introduce a technique which we will be using mostly for derivations. It's not going to be part of the major final equations that we use, but it will come up fairly often in this chapter, and it's called Huygens principle. To understand it, we need to know what the idea of a wavefront means. And when you have a propagating wave, you can look at it from the top and see where, for example, all the maxima and all the minima of your oscillating wave are. And if you look at it from the side, you can see both aspects of it. You can see the straight lines at the top and the oscillating nature when you look at it from the side. These lines that are perpendicular to the direction of the motion are called wavefronts, and they play an important role in Huygens principle. Huygens principle, in fact, states that every point on a wavefront acts as a source of little waves that are typically circular or spherical that spread out in the direction in which the wave was going. And then after some time, t, you look at the tangents of those wavefronts, and you connect all those tangents, and they give you a new wavefront. And we can take, for example, here from where we were, draw a new set of wavefronts originating at every point in the old wavefront, and we generate a new wavefront later on. So it's going to be a sequence of parallel lines, just as we had seen in the earlier picture, in the previous picture. You can use Huygens principle to draw the wavefronts that correspond to, for example, reflection on a flat mirror, and the incoming wavefronts will look vertical. But after you bounce off the mirror, you get now horizontal wavefront. So your wave now is traveling downwards. So it was coming in from left to right, and after it bounces off the mirror, it goes downwards, which makes a lot of sense. And it's a sign of consistency that you can get at from Huygens principle. A slightly more sophisticated case is refraction, where you look at different indices, materials with different indices of refraction, and you see that, for example, at this point, well, let's look at these 2 points. One of them is already propagating the wave in the medium with a smaller wavelength, so the little wavelets don't travel quite as far. And what that causes is light appearing to bend, as we know it does with refraction. But to talk more about the purpose of this chapter, which is the behavior of light in the presence of smaller objects that can be slits or circular holes or different things. If we apply Huygens' principle, say to a wave front coming towards a finite slit, and this is a top view and there's like an opening, if every point acts as a wavefront, near the center of the slit will get the expected kind of vertical wavefronts, but at the edges we see that the light bends. And this is a phenomenon called diffraction, which we'll talk about in more detail a little bit later in the chapter. The double slit experiment was important. In Newton's time, Newton thought light was made of particles, and there were experiments that showed the wave nature of light. Nowadays, we've accepted that both have something correct about them. There is not a complete unified picture of light, although people have been working at it, very, very good scientists for a long time. And the Young experiment consists of having light go through 2 slits. So you make openings, very narrow openings, kind of probably less than a micron, and you shine light. It has to be special light that is coherent in some ways, like a laser. And you see a pattern emerging in a distant wall. That light doesn't just form too bright fringes or too bright zones in the receiving wall, in the screen where the light is being collected, but rather you get a more complicated pattern, a sequence of bright and dark vertical zones that, as we will see, can be explained by having light being a wave. So before we get there, we have to review something from your Physics 151, in which when you have 2 waves of light arriving, and this is a picture as a function of time, so you have an amplitude versus time. When the 2 waves that arrive to a single point are synchronized, you add their amplitudes and you get a stronger wave, a wave with a larger amplitude. However, if the 2 waves are totally out of sync, one has a maximum while the other one has a minimum, you see that adding the positive and negative values, or in this case 0 and 0, or in this case very highly negative with very highly positive, they always cancel and you get essentially a result of no wave at that particular point. The top case is called constructive interference, and the bottom case is called destructive interference. And I think those names are fairly self-explanatory. So when you have 2-slit interference, you can get a global picture. You can imagine wavelets originating at each of the 2 source points and interfering or interacting with each other, and you're going to get regions of very strong constructive interference and others of very strong destructive interference. But once you get to a wall far away, what you'll observe, as we said, is this sequence of dark and bright spots. And this is an actual picture of 2-slit interference done with a laser. One can do a little bit of math with this, and what we'll have is our 2 sources. We'll have a separation between our two slits. We'll have a screen far away capturing the light. And there will be points where the waves that come in are synchronized, and you'll have then bright spots with constructive interference. And there will be other places where the two wave trains are completely out of sync, as shown here. One has a maximum, one has a minimum, and you get a dark spot instead. And it's figuring out at what positions you get the dark and the bright spots. That will be the next argument and the next calculation we do. So this is the essential picture. And what we have here, let me move this a little bit to the side, is our two paths that the two emitted waves follow. And as you see, very close to the source, we have then now defined the distance between the two slits as lowercase d. And we have an angle essentially between the midway point between the slits and the point where we want to see what the light is doing. So we have this angle theta, and we can draw this little triangle with D here and a 90-degree angle. And the difference in length between the two paths is going to be this little piece D sine theta. So the theta that I defined here and this theta are the same. You can do a bunch of those equivalent triangles. And now if that extra distance traveled by one of the two waves is an integer number of wavelengths, the two waves are going to arrive with their maxima coinciding. It's not going to be the same maximum. Say the one that had the shortest path, maybe that's one maximum coming from the wave that was incoming from the left. And for one which has to travel an extra distance and then therefore longer time, maybe that exact same maximum is one or two maxima away in space and time. But the screen doesn't care as long as maxima arrive at the same time. It's constructive interference. On the other hand, if the difference in path is half a wavelength or 3/2 or 5/2, you get this here. And if your d sine theta is equal to that, you get destructive interference because your waves now arrive completely out of sync. One is at a maximum when the other one is at a minimum, and vice versa, as we saw before. So the main formulas for two-slit interference are given here, 27.3 and 4. One thing one can do to accentuate the pattern is instead of having two slits, you can have 5 or 10 or even tens of thousands. And when that happens, the original pattern for the double slit that looked a lot like this function with the successive maxima and minima now becomes a lot sharper and more pronounced, and it looks instead something like this, with some of these oscillations in space now being of quite small amplitude, and then you get some huge peaks. And that's useful when you're doing things like spectroscopy, when you want to analyze what the wavelength of your light is by passing it through slits with a certain separation between them. You want to have really sharp, bright lines so that you can measure them easily, instead of having that more fuzzy pattern that we saw earlier. It turns out the math is identical, and you also get d sine theta equals m lambda for the bright spots for the constructive interference. So let's talk a little bit now more about these diffraction gratings when you have light going through multiple slits. And as you see, the kind of the geometry is exactly the same. You get your triangle, the hypotenuse is D, you have your angle theta, you have the difference in the paths and so forth. But these things are hard to make if you're trying to do slits, to carve out slits that are very narrow and very close to each other. This would be technologically very difficult. What you do instead is you have a, you make up a surface which looks like this. So instead of having light go through the slits and come out on the other side, you actually bring light from one side and have it reflect on little mirrors and then come out and create, you know, a pattern on your screen. This is much easier to make because all you have to do is now have a hot surface that is malleable, that changes shape, and you pass a roller through it with kind of the shape in which you want those mirrors, and you can make this in a matter of seconds, let it cool down and solidify, and you're all done. And one little detail here is that you typically describe these diffraction gratings not really by D, but by how many lines or kind of replicas of that mirror shape that I showed you, you have per centimeter or per meter. So if you have, say, 10,000 lines per centimeter, the separation between two consecutive lines is the inverse of that, or 1 centimeter divided by 10,000, which is 10 to the minus 4 centimeters, or 10 to the minus 6 meters. So you often have to do this conversion from the way the data is presented to you to the way the data can be actually put into the equation. Let's go back to our original problem, which we had talked about. What happens now when you get a single slit and you observe the bending around the corners. So this time we're going to pick a different symbol, an uppercase D, for actually the width of a single slit. And what we will see is that a pattern forms that looks superficially like that of the two-slit interference, except you get a single huge maximum and then kind of a lot less dark maxima, kind of alternating with minima where your pattern is dark. And it turns out, so to give you some advance, the math here becomes a lot harder because what you do now is, instead of just having two sources for your wavelets, wavelets are forming essentially at every point inside your wide slit. And what you do is you do a similar geometry to what we had before with your D, uppercase D sine theta. But the story now is you don't just have two sources doing constructive or destructive interference. What you have instead is an infinite number of them. And you have to start saying things like, okay, if I pick my width to be like this, maybe something that is half that distance away, so lambda over 2, I can start taking pairs of paths that are lambda over 2 away from each other, and those will interact destructively rather than constructively. So interestingly enough, the formula that gave you the maxima before now gives you the minima. So you have this expression, uppercase D sine theta equals m lambda, is now the condition you require for destructive interference. So if you want to look at a single slit of width D and see the pattern you're forming here, you can identify these dark areas. You can find the respective angles where the dark areas are by using this particular formula. The maxima now are very hard to calculate mathematically, and this is done, for example, in upper division optics courses, but it's something that doesn't concern us right now. Moving on, kind of long, thin slits are very interesting and they're very doable mathematically. But what we want to do in this section is think about our instruments from the previous chapter, telescopes, microscopes, and magnifying glasses, as being like slits themselves or being openings. They're circular openings rather than elongated slits. And they also are affected by diffraction, and that gives you a limit on the quality of your instruments. In fact, it's very common that the diffraction limit is what defines how useful or how poor your optical instrument is. Think of it this way. Each source of light that you're looking at, or your microscope or telescope, will have a diffraction pattern, but instead of being now a maximum followed by minima on both sides, it's a two-dimensional pattern with a bright circular center and then alternating rings of bright and dark. And you are concerned with the big bright spot in the center, because if instead of looking at one source of light, I'm looking at two of them now, their diffraction patterns, if the two objects are too close, will overlap each other. When they're far enough apart, you can really say, okay, I have two objects here. I can see, you know, a little narrowing in the brightest pattern, so I know I'm looking actually at two things. But when your objects get closer, like here, your sources of light, you see now a pattern that could be either a single object or multiple objects, and you are no longer able to distinguish individual sources of light when you're looking at them through your telescope or your microscope. And this is the diffraction limit. It so turns out the math is hard. Again, junior level physics course, physics and astronomy. But it turns out you can find the angle of separation so that two of these circular patterns of rings still allow you to decide or to discern whether you have two sources. And that is a function of both the diameter of your instrument, of your magnifying glass or your eyepiece or whatever it is, the wavelength of light you're looking at, and the mysterious factor of 1.22 that comes after one has done about an hour of fairly advanced calculus. But it's doable, but it's not within the scope of this class. So that's what tells you when two of those patterns overlap enough that you cannot tell whether you have one object or two, or when if the separation is at least that angle or greater, you're fine, you can tell you have two separate objects. So we have two topics left in this chapter. One is thin film interference, and this is this has some common elements with the two slit interference, except it's a little bit different. What you have now is typically a film made out of some transparent material, can be oil, can be plastic, can be glass, and you have two other media, 1 and 3, above and below that. So you could have something like a thin layer of soap with air on both sides, so N1 and N3 will be very close to 1, or maybe N3 is a camera lens and N2 is an anti-reflection coating separating your lens from the outside world, where N1 would be corresponding to air again. So what we want to do now is calculate the path differences, just like for two-slit interaction. But what we have is a ray of light coming almost perpendicular, and the closer to perpendicular, the better. Some of it reflects back, some of it gets refracted into the second medium, where it's reflected back at this end and comes back towards your eye, and some of it gets refracted again into your third medium, goes away forever, and it's not really part of an interference pattern. So for the two that you have, clearly the path that goes into N2 is going to be longer than the one that goes just to this first interface and bounces out. So what you want to do is calculate the difference between these two paths. And that will tell you whether you have constructive or destructive interference. So there are two effects. If the thickness of this film is T, the ray number 2 is traveling an extra distance to T, but you have to take into account that when you move into medium 2, your wavelength, which was some lambda 1, now becomes a lambda 2 because you have a different index of refraction. And let me refer you to the very, very first formula we talked about in this video, which relates lambda sub n, c, and lambda and n. And essentially you have a different, your light is going slower in a medium of higher index of refraction. And since the frequency doesn't change, your wavelength also has to be shorter. The second factor is what exactly happens at the point of reflection. And you have two situations. You have a situation in which your the index of refraction at the point where you are reflecting, or the surface onto which you're reflecting, in this case it will be N2, and in this case it will be N3. If N2 is less than N1, the reflection happens with essentially no consequence. But if N2 is greater than N1, there is an extra shift in the waveform that flips it 180 degrees or half a wavelength. That's essentially the same thing. If I have something like this and I shift it by half a period, the period being 360, so I shifted half a period, now my maximum will be here and my minimum will be here. So I have done essentially the same thing. So either 180 or half a wavelength has the same meaning in this case. So the secret for this type of problems, and we will do one or two in a subsequent video, is to add all these factors correctly, like by how much does the actual trajectory increase in terms of number of wavelengths. So 2t, the extra distance traveled, is equal to how many lambda sub n's, and is there a lambda over 2, yes or no, factor of shifting at each of the two surfaces. If one has it but the other one doesn't, you take it into account. If both of them do but neither does, there is really no relative change between the two rays and you're fine. So that's essentially how you treat your thin films. And very often, for example, a thin film needs to be designed so it reflects very well one wavelength but not another. Maybe you want something that reflects back to you the green light or the red light or something like that, and absorbs all of the others. This would be something like a filter for a movie, for a camera or movie lens. In other cases, you may have other applications in mind. So this is kind of an interesting one, and it is when two lenses are put together, so there is the air gap between them is different at all points, and you get these very nice patterns where different colors show up at different locations, and you can kind of work this backwards and see whether the shapes you wanted for these lenses are exactly what you had in mind, or whether you have to keep polishing. So that's enough for this topic. There is one more, which is polarization. You probably have heard of it, polarized lenses and so forth. And polarization comes about because when light is traveling in a certain direction, say here it's going to mostly to the right, we have, as we saw a couple of chapters ago, I think in chapter 24, that you have perpendicular electric and magnetic fields, but you have an extra kind of degree of ambiguity, and it is that if I look at the direction in which my light is coming at me, the electric field could be pointing in any direction, not just the direction shown there, and that's essentially the polarization of light. And the B field will follow at 90 degrees to the E field. So once you have a direction of travel and your E, your B really doesn't have any choice on in which direction it points. It's with this polarization, with the direction in which the electric field is pointing, that you can do some really interesting things. So let me move on and tell you there are several ways to polarize light. In other words, to take a disorganized mixture of polarizations, something like the bulb you see right over my head. It's kind of an LED bulb. It produces light of many different frequencies, many different polarizations. Even the waves that come to you are out of phase. They don't reach the maximum at the same time. So it's very disorganized light, and it's not very good light, for example, to do two-slit interference and stuff like that, because there is no pattern to it to start with. However, I can take light like the one up here and pass it through what's called a filter, and that filter will select a direction of polarization, and the direction of polarization that it lets through is called the axis of the filter. And the way these filters usually work is they actually have a long polymer, a conducting polymer, oriented in the perpendicular direction. So when light comes in at all polarizations, the light that is oriented in the same direction as the polymer will be absorbed by the polymer, and it will set all kinds of electrons moving back and forth. It'll be kind of like an antenna receptor, but the light that's coming perpendicular in the vertical direction will not interact with the polymers, and it will go straight through. So we define a filter by the direction of the light that manages to get through, not by the direction in which the polymers are oriented, which is perpendicular. So there are some, this shows everything I told you about except the polymer itself. So it shows you a typical polarization or polarizing filter. And this is kind of how it works in practice. When you have unpolarized light coming into a polarizing filter, its intensity decreases by 1/2 exactly. So I here is going to be 1/2 of I here. So just by polarizing light, you lose half of the intensity. power per unit area. And that's what your polymer filaments acquire and get to use for a while, and then it gets dissipated in other ways. Now, once you have polarized light and you put it through a second polarizing filter, if the axis of the filter is aligned with the direction of the polarized light, all of it goes through. However, if you put it at an angle, there is a new process of absorption of light, and then the new twice polarized light comes now in the direction of the second axis. And what's more dramatic is if you make light go through two polarizing filters that are perpendicular to each other, well, the first one acts and what you expect happens. You get light polarized in the vertical direction, say, but now that light interacts with polymers that are vertical, and essentially all of it is absorbed, so none of it gets through. If you're at an angle that is not exactly 90 degrees, some of the light gets through, otherwise none of it gets through. And that is captured by this formula that tells you that once you have already polarized light with a certain intensity, and you put it through a second filter for which the axis of polarization is at an angle theta with respect to the original polarization, the one in the middle, only so much gets through. And when the angle is 90 degrees, you get nothing. And figure D kind of shows that nicely. There is one filter in the back, which is the central one. Then you put one on your right that is at 90 degrees. And as you see, essentially nothing gets through here. And this lens here is placed at some angle in between, so part of the light gets through, okay? Or actually almost all of it. Polarization can happen in other ways, in natural ways that don't involve filters. One of them is reflection at surfaces like water or even roads. When light comes in and hits a horizontal surface, essentially the light also interacts with the atoms in the surface itself, and a lot of the horizontal component gets absorbed. If it's reflecting into a horizontal surface, the component this way gets absorbed because, again, it sets things in motion in the atoms and molecules of that surface. And what comes out is largely vertically polarized. This is easy to see when we had face-to-face classes. I could do it with a regular whiteboard and your overhead lights, and just pulled out a polarizing filter and showed you that that light responded to the orientation of the filter, showing that it is polarized. Another very practical example of this is driving glasses, polarized glasses like sunglasses, which are largely designed to deal with the reflections from the road back into your eyes. And what they do is they absorb the vertically polarized light. So they're partly or mostly horizontally polarized sunglasses. So they capture a lot of this light, so the intensity that reaches your eyes doesn't blind you or make you see things that are not there. I'm not going to talk about the Brewster angle. There's a third mechanism of polarization, which is just sunlight hitting random molecules in air as it gets to us. It partially polarizes light, and sunglasses are also good for that. This concludes the lecture part of chapter 27. Thank you.